Okay, everyone. So our topic would be about air masses, and then we also have fronts, and then afterwards we will have the mid-latitude cyclones. So let's start. Let's define first what is an air mass. When we say air mass is a volume of air defined by its temperature and water vapor content. Air masses cover many hundreds or thousands of miles and adapt to the characteristics of the surface below them. Now, is a volume of air which has uniform temperature and water vapor content. Okay, such a mass has distinct boundaries and may extend hundreds or thousands of kilometers horizontally and sometimes as high as the top of the troposphere, about 10 to 18 kilometers above the Earth's surface. Now let's take a look at this map wherein you can see here the labels MT, MP, CT, and MP. Let's define each of those air masses. We have the maritime polar air mass. When we say maritime, that means it's a layer of air above water. So it's coming from water surface. It's polar since it's coming from the polar regions. So it is coming from water. So it's also cold because it's coming from polar region. And then since it's coming from water surface, it carries with it water vapor content. So it's a moist air mass. MT, we have here the maritime tropical. This since again it's still coming from water surface, so it is still moist because it carries moisture with it. But if since it's coming from the tropical, so it's warm. So we can describe it as warm and moist. CT, that is continental tropical. So if it's coming from continents, so you don't have much of air moisture there, so it carries with it dry air. Since it's tropical again, it's dry, hot air, the CT or the continental tropical. Then we have the continental Arctic. Since it's coming from the Arctic, it has a very low temperature, so it's very cold. However, since it's coming from landmass, it has no moisture with it or less moisture with it, so it's considered to be dry air mass. Then the next one is the continental polar. So again, coming from the continent, so it's dry, but coming from the polars, therefore it's cold air mass. So other examples are this. We have here polar maritime air mass. This is coming from Greenland or Arctic Sea. It is wet, so it has high moisture content. Cold air, which brings cold showery weather. Then we have here the returning polar maritime from Greenland or Arctic via North Atlantic. It is moist, mild, and unstable air bringing cloud and rain showers. We also have another example, the tropical maritime air mass. It is coming from Atlantic. So it's tropical, therefore it's warm, but it's maritime, that's why it's moist air, which brings cloud, rain, and mild weather. Then you have here the tropical continental air mass coming from North America. Since it's a continental air mass, so it brings with it dry air. Since it's coming from tropical, the temperature is high. So we have hot, dry air, which brings hot weather conditions in summer. And then you have here the polar continental air mass. Polar, so it's cold. Continental, therefore it's dry. Coming from Central Europe, you have here hot air brings dry summers. Cold air brings snow in winter. Then you have here Arctic maritime air mass. So it's coming from the Arctic. This is also cold. And then since maritime coming from bodies of water, it's wet. So it's wet. Cold air brings snow in winter. So those are examples of air masses. Now let's move to the different fronts. Okay, so now let's talk about mid-latitude cyclones. Let's define it first. Mid-latitude refers to the area of North America, roughly between southern Alaska and Florida. And when we say fronts, these are boundary surfaces that separate air masses of different densities. one of which is usually warmer and then contains more moisture than the other. It can also form between any two contrasting air masses. Any temperature difference can define the front. Sometimes fronts separate air masses of different humidities. Fronts are also classified as to which type of air mass is replacing the other. Anyway, we will discuss one by one each front. Then when we say overrunning, it is the process of warm air gliding up and over a cold air mass. The following are the types of fronts. We have warm fronts, cold fronts, stationary fronts, occluded fronts, and also dry lines. Okay, I want you to look at this animation. Okay, that's a warm front. So you can see here in the animation that what happens, you have warm air mass, and then it's trying to replace the cold air mass. So as we know, if there's temperature difference, the warmer air will rise. Okay, so as you can see here, warm air rises, and it's trying to replace the cold air mass. Now, at the edge of the cold air, there is an expansion or the adiabatic expansion. When we say adiabatic, no heat is added or released from the system. However, pressure was released or pressure it was decreased. Therefore, it can expand. The volume will increase. That's why we have here the formation of clouds. Okay, now you can see here that when surface position of a front moves so that warmer, moist air invades the territory of formerly occupied by cooler, dry polar air mass. I will show you a symbol used for this. We have the red one with semicircles. That is the symbol used for warm front. And then for here, we have triangle and blue ones, cold front. If you have alternating blue triangle and then red semicircle, you have stationary front. And then for this, the purple one, we have occluded front. So those are the symbols used. Now, as you can see here again, warm air rises, then it's trying to replace the position of the cold air mass. So what happens here? There was an expansion, as I have mentioned, and then there's the formation of clouds. So from cirrus clouds, then it will become cirrostratus clouds, and then it can become altostratus until it becomes nimbus stratus clouds. So that may result to moderate precipitation. Okay, so we have here warm front in a conditionally unstable air. When we say unstable, that means the warm air continuously rising. So it can produce altocumulus and then cumulonimbus clouds, which can result to heavy precipitation. Okay, so take note that warm front in a conditionally unstable air can produce heavy precipitation. Take note also that during winter, warm air above a sub-freezing air or very cold air can result to formation of ice or snow, because raindrops can be super cooled as they fall through the sub-freezing air. So it can produce freezing rain or glaze. The following are the weather elements or the weather conditions which happen before passage of the front and also after. So initially, you have cold air, and then after it will be replaced by a warmer air. The dew point is moist and rising, and then you will have higher dew point after the passage of the warm front. The direction would be initially east, and then after the front, we have the direction moving towards west. Then before passage, the pressure is actually falling, but after passage, we have rising pressure, because we have mentioned warmer air replaced the cold air. Then for the clouds, before passage, we have cirrus, we have cirrostratus, altostratus, nimbus stratus, stratus, and possible fog. But after the front, we now have clear with scattered stratocumulus. For the precipitation before passage, there's light to moderate ahead of the front, but after, there's no precipitation. Now let's take a look at cold front. So what do you observe here? For the cold front this time, the cold air pushes the warm air. And then it becomes steeper and steeper. As you can see in the illustration, as it moves, it becomes steeper. Cold front is also faster than warm fronts. So again, this is another illustration. We have cold air now, this time replacing warm air. Cold fronts also result to heavy precipitations. They are associated with thunderstorms. Again, cold fronts happen when cold, dry, stable air actively advances into a region occupied by warm, moist, unstable air mass. The symbol used for this would be blue line and blue triangles. And then we also have, as I have mentioned, cold fronts steepen as they move. They are also moving very fast. They are 50% faster than warm fronts. Then cold front produces roughly same amount of lifting as a warm front, but over a shorter distance. That's why it's being pushed so that it will become steeper. And then precipitation also is more intense compared to warm front, but at a shorter period of time. So this results to unstable air and results to heavy precipitation, thunderstorm, lightning, and even tornadoes. Now let's take a look at the different weather elements. Before passage, you have their warm air mass. Then after, it will be replaced by colder air mass. The dew point initially was high. After the cold front, we have lower dew point. For the wind direction, initially it is south. After passing, we have west-northwest. And then pressure also was initially falling, but after it has passed, pressure rises. And then for the clouds, we have cirrus and then cumulonimbus. After the cold front, we can have clear sky or we can have cumulus clouds. Then precipitation, we have heavy precipitations at the cold front, and then after we have decreasing precipitation. Okay, now I want you to look at stationary fronts. What do you observe here? In the animation, you can see their cold air mass meeting warm air mass. So that is stationary front. Transition zones between two air masses that are not moving or they can be moving very slowly. Then boundary will have few rain showers and thunderstorms. They are represented, as I have shown you earlier, they are represented by alternating sections of cold and warm front symbols. So it's alternating blue triangle and red semicircle. So that is for the stationary front. Okay, so let's explain the occluded front. Now, I want you to look at the animation. So what happens here is the formation of the warm front. So you have two cold air masses. In the warm front, we have mentioned that warm air replaces the cold air. So it is moving upwards. However, it's replacing the cold air mass. But what happens again is another cold air mass will be pushing that warm front. So we have here, as you can see here, we have another cold air mass. We have the warm front here. And then that cold air mass will push the warm front. So that means it also happens, and it also happens very fast. So it will result to cumulonimbus clouds and also results to heavy precipitation. So that's for occluded front. It's a rapidly moving cold front overtaking a warm front. So those are illustrations or pictures of occluded fronts. Then we have a cold type occluded front wherein cold polar air mass now meets the maritime polar air mass. And then warm air rises. So that results to cumulonimbus clouds. And then another one would be the warm type. What happens here is the maritime polar air mass pushing the cold polar air mass. So that is the warm type occluded front. Cold type occluded front produces thunderstorms, and warm type occluded front frequently occur along the Pacific coast, where milder maritime polar air invades a more frigid polar air that had its origin over the continent. Now let's have dry lines. Drier air, take note, it's denser. Why? Because we have mentioned that um, we have, let's say, the nitrogen, the other components of air, they are considered to be heavier compared to water vapor. So when the water vapor was replaced by those elements or by those components, it will become denser. That's why dry air is denser and forcefully lifts the moist air in its path. It's just like warm and cold air. Warm air rises, cold air sinks. But this time we have drier air sinks, but moist air rises. Dry lines happen in the areas when there is a sharp drop in the humidity. Okay, now let's talk about the life cycle of a mid-latitude cyclone. So you have here the formation. So the formation of a mid-latitude cyclone, it starts with the clash of two air masses. And then we have the second stage is the development of cyclonic flow. The next would be the mature stage of a mid-latitude cyclone. And the last one would be the occlusion. Okay, so let's discuss each. Okay, now I want you to look at this animation. Okay, so you have here, you can see here that it involves the formation of cold front and then warm front. So let's take a look at the different stages. So based on the symbols here, you have a cold front here and then a warm front here. This is the initial stage, wherein the front initially develops. So you have cold front and then warm front, or cold air masses and warm air masses, and then it starts to move. So we have mentioned that warm air will rise and then cold air sinks, and then it will start to develop a wave. Then after that, we have here warm front and then cold front. So this one will start to move, or we will now have the cyclonic circulation being established. As you can recall, warm front means that warm air replaces the cold air, and then for the cold front, the cold front now pushes the warm air upwards. Okay, you can see here that there's no occlusion. Based on the symbols, we only have cold front and warm front. So we now have here cold front in this area, and then you have here warm front. And then after, there will be occlusion. The occlusion begins. So you can see here the symbol for occlusion, the violet one. Now occlusion begins again when you have warm front and then it's being pushed by the cold air. Okay. So occlusion continues to develop. So occluded front developed. And then afterwards, you have here the cyclone dissipates. Now what happens? It is creating a lower pressure area. Since we have mentioned that warm air will rise, so it will start creating lower pressure area. And then when we say we have lower pressure area, remember that in Bernoulli's principle, what's the relationship between the velocity or speed of wind and the pressure? The lower the pressure, the faster will be the velocity of wind, or the faster will be the movement of air. So at the lower pressure area here, this will be moving faster. And then what happens? We have convergence and divergence. So we have mentioned that warm air rises. So at this point in the mid-latitude cyclone, at the upper point, we have here divergence. As this one continues, so there will be divergence, warm air will be moving outward, then cold air will be replacing that. So there's a continuous movement of air. So this will deepen it will deepen our cyclone or air. So until we will now have higher pressure. If higher pressure happens, that means that the air will be moving at slower rates, and then the cyclone starts to dissipate. Remember that when there are weather forecasts, when they say low pressure area, then that means a storm is developed. Take note also that the rotation of the air for North Hemisphere, we have the counterclockwise rotation of the air, or we have the cyclonic rotation or cyclonic movement of the air. So again, it's formed because the cyclone is born when two air masses of different densities, particularly different temperatures, are moving parallel. However, they are in opposite direction. Then convergence and divergence patterns aloft are extremely important. So we have here convergence when air passes up, and then divergence when air spreads out. However, as I have mentioned, diverging air aloft will deepen the cyclone. Okay, so you have here warm air moving poleward and then cold air moving equatorward. So there is now the formation of cyclonic flow or counterclockwise flow of air. So take note, this is in the northern hemisphere. We have the counterclockwise circulation. Then at the mature stage, the pressure surrounding the low continues to drop, causing winds to strengthen. I already have mentioned this, that the lower the pressure, the faster will be the wind or the air, and frontal weather to develop. Okay, next would be the formation of the occlusion, wherein we have here, when we say occlusion, cold air pushes the warm front. So occlusion occurs. Usually also cold front advances more rapidly than warm air. Then it will overtake the warm air as we discussed during the discussion of the fronts. Then occluded front is formed, then storm intensifies. As I have mentioned, this one as warm air aloft, the surface pressure gradient weakens and so does the storm. Okay, to summarize the formation of the mid-latitude cyclones, we have this. It begins as low pressure areas along the polar fronts where warm air meets cold air. Then the wave develops, initiating a separate warm and cold front, and then pressure becomes lower. As the storm intensifies, pressure continues to lower and cyclonic in the northern hemisphere. We have a counterclockwise direction or counterclockwise flow, then it increases. At the point of occlusion, the storm is at its greatest strength. Then it will decrease its intensity. The storm dissipates and fronts disappear. The storms also travel in a general west to east direction. Okay? So that is the life of mid-latitude cyclones. So that would be the end of the discussion. We will schedule a quiz for these topics. Okay? Bye everyone.